And I got it. So this is work that I did with Jordan Mora, who you heard had worked here previously. And just to give you a little bit of an intro into my background, if we can get the slides to advance, what I'm doing, page down.
Page down and just
wait. Maybe. I'll just talk about this slide the whole time.
Try it again. I don't think there's that much of a lag. I think it's just. Try return.
Try return?
Yeah.
Oh.
Try arrow.
Well, this will be a short talk. Sure, if you want.
Yeah.
So I was going to tell you about my background. I started out in Minnesota when I was born. I'm the first millennial. How did you do that?
I hit it hard.
Hit it hard. All right, got it. So I was born in Minnesota. I lived there for about my first decade. Then I moved on to Pennsylvania with my parents, of course. Around the age of 15, I saw the ocean for the first time. So to give you a little context of my background growing up in the Midwest in Pennsylvania, became an Eagle Scout along the way, somewhere there. Went on to college at a small liberal arts school called Albright College in Reading, Pennsylvania. Did my first presentation, just like this one, on endangered bog turtles. Went on to the University of Virginia, where I did my master's and my PhD. That's the presentation from my PhD defense that you see there. Worked a lot in coral reefs, seagrass beds, went to Greenland and did work on ice sheets, and started developing a lot of technology at that time. And I've been on Cape Cod for about the past decade. I've been working out here in Waquoit. I do a lot of technology development, a lot of instrument development, and there's a presentation from today's slide. So just a little bit about how I got here, and we can advance now. Magic, great. So a little bit about what motivates me. I'm really interested in charismatic photosynthesizers. So what is that? That's green stuff that makes oxygen, right? These are plants that grow in the ocean. It can be corals that have plants in them. And these are hotspots of biodiversity. They're nursery grounds for fisheries. They store blue carbon, which is a very hot topic right now as we try and get the carbon out of our atmosphere and back into the environments where it should be. But these environments are also really influenced by both local stressors and global stressors. And I'll talk about both of those today, right? So our local stressors here are nutrient pollution that we see in our waters every day. But we also have global stressors on top of that. We have global warming, we have deoxygenation, less oxygen in the water, and of course we have ocean acidification. Our oceans are becoming more acidic. So a little bit more about my motivation. What you see in these two slides are plots of pH, so that's the acidity in the seawater, and oxygen content, right? Everything needs oxygen, we need oxygen, we're breathing oxygen right now. And I have this from two sites, one out in Martha's Vineyard, just off the coast of Martha's Vineyard, which is the one on the left. And then I have it from Waquoit Bay, right in the middle of the bay out here. And what you see is that offshore, off of Martha's Vineyard, it's pretty consistent, right? But when we come into Waquoit Bay, we get these really big daily swings, right? And that's because there's a lot less water in here. There's a lot of respiration. There's a lot of primary production, that oxygen production by plants. And that causes this very big variability on just a daily basis. So what motivates me is really understanding why that is, how it affects the organisms that live in the bay, and ultimately what it means going forward in the future. So I've highlighted a couple of factors here. All of these factors go into driving that variability of the water quality that we see out there. But the ones that are going to be important today that I'll talk about are benthic primary production, right? So what are the plants doing that are living in the water? What's going on in the water columns or the phytoplankton in the water that are just microscopic plants that are making oxygen and taking in CO2. Residence time is very important. How long does that water stay in the bay? How much is it flushed in and out with the tides? And then of course, nutrients is something today. So I do a lot of ocean engineering. All these are instruments that I've built over the last decade or so. The ones you see highlighted in red are actually things I've tested right out here in Waquoit Bay. So I develop all these instruments in my lab with a whole team. I develop a lot of new technology. That's the focus of what I do. And what that results in is tons of data, right? So I'm very good at taking lots of data, distilling it down, and making a picture out of that and telling a story. And that's specifically what I'm going to do today. So with Jordan's help and a little bit of history about the program, we really dug into all the data that's been collected here over the last 30 years, and even beyond that from some historical records. So what drove me to do that analysis? Well, COVID hit. We had a lot of canceled cruises. We had a lot of canceled trips that were supposed to be all throughout the world. So I grabbed a couple of graduate students and said, hey, I know where there's some cool seagrass beds out in Waquoit Bay. Let's go out there. You can do some component of your research. It's local. It'll be fine. We can take kayaks. We can do it really easily. So we came out to Waquoit Bay to work in the seagrass beds out in Sage Lot Pond. We didn't find it. Right? So I called Jordan and I said, hey, what's going on? Where's all the seagrass? And that kind of led us to where we are today. So we started digging into a lot of the historical data to really get, an understanding what the historical perspective was here. Like, what did Waquoit Bay really look like 75 years ago, right? What is that baseline environment that we should actually see? And then we wanted to bring in all the new technology, all the monitoring that's been going on here at the reserve, and really help make sense out of all this. So what you'll see in the top figure there is scallops harvested, right? Mid-90s, scallops are pretty much gone from the Waquoit Bay, right? Again, not a great picture. In the bottom series of figures, these are from Joe Costa's thesis, actually, except for the one on the right. This is that decline in seagrass that you can see over the years, and starting in the 50s, going up into the late 80s. And from the state's monitoring program, where they do it from aerial surveys with airplanes, the last place in 2015 where we really had a lot of seagrass was out in Sage Lot Pond, which is that seagrass bed that I plan to take graduate students out to work at. So we didn't find anything. I talked to Jordan. I said, hey, can we make the surveys happen out in Waquoit Bay? These are surveys where they go out, they do drop samples, and they see what's on the bottom. They pull up that algae, they pull up that seagrass, and then they actually quantify how much is there. We didn't find any eelgrass or scallops in 2020 when we did those surveys. So it doesn't mean it wasn't there. That means we didn't find any in the places we looked. So taking a step back a little bit and looking at excess nutrients and loss of seagrasses. This is not just a Waquoit Bay problem, right? There's seagrasses that are in decline throughout the world, in the tropics, in Europe, everywhere. And globally, a soccer field of seagrass is lost every 30 minutes. Right, so this is a community that, sure, it's in decline here locally, but it's really in decline globally because of the same set of problems. And one of the main things is excess nutrients in those environments where they grow. They grow in shallow water, they go near shore, and that's where we're putting all the nutrients into the water. What you see in green here is that eelgrass extent from Joe Costa's PhD thesis that they went back into old aerial imagery and figured out. And you'll notice that there's no green in all the little embayments around Waquoit Bay. Why is that? That's because they were too small to matter, right? They didn't even analyze those small embayments because there was so much grass in the middle of Waquoit Bay. The only place that they found them in the most recent aerial surveys were in a few spots in those little tiny basins that they didn't care about in 1950 because they were just too small to matter. So again, not a great picture. 98% loss just based on that right there. So we've all heard about this. This is that 85% of the Cape uses septic systems to get rid of the wastewater, right? Pretty much everybody's house here has a septic system attached to it, right? And of course, all the news stories recently about how the state might be trying to implement denitrifying septic systems. And we'll talk a bit about that later. But the main problem is right in the center, right? This map of Cape Cod shows the current sewering that's been done in Falmouth, right? So the little green lines and most recently the orange lines around Little Pond, that's where the sewers are. When do we expect to see sewering here? 2040 on a positive side, maybe? So it's quite a long ways out and water quality is getting worse. And how do we address this? Well, that's the larger question, right? So getting into eutrophication impacts. So what is eutrophication? That's just too much of a good thing, right? Everything needs nutrients to grow. We all need nutrients to grow. We just simply have too much of them here. So these are time series from Joe Costa's work and Ivan Valiella's work, where we see this decline in scallops through the years. And those axes are logarithmic, which means that change is really, really big, even though it doesn't look like it, right? Those are factors of 10 decline. We see the same thing that we see in scallops, we see that in clams also. This is some work from Linda Deegan that also works just up the road in Woods Hole, showing the abundance of fish and small crustaceans that are living in the water and how that relates to the amount of nitrogen loading on the bottom. So when you get more nitrogen into the system, you get decreases in the abundance of all the organisms in the water. So looking a little bit about the work that we did, this is a figure from our paper. Megan introduced all this earlier, which is great. I'm going to focus on 3 sites in Waquoit Bay. Childs River, which is right back here, circled in red, Metoxet, which is right out here in the middle, and Sagelot Pond, which is just inside of the coast out there. And these are seagrass abundances in hectares in the figure on the right. And we have data going all the way back to the 1930s, right? And these are different portions of the bay. These are different sites, most of which are on the map there. But you can see, you know, where we are today, right? Right out here. There's pretty much nothing out there. So one of the things that happens when you lose eelgrass is you get a growth of macroalgae. You've probably all seen this out in the bay. There's a couple pictures there. You get this really robust green or red growth on the bottom. And what the figures are showing here is just, again, the amount of nitrogen on the bottom axis and on the left, that amount. And you can see that as we have more nitrogen in the system, we get more macroalgal growth. So seagrasses we lost, they really got replaced by macroalgae as the dominant primary producer, that dominant plant making oxygen and taking in CO2. So we looked a little bit deeper into the data, and is this really what we're seeing right now? Are we seeing more macroalgae growth? And this is another figure from the paper, and what you see on the left is algal biomass from 2004 to 2020. What does that say? It's going down, right? That's what we're finding right now. The middle is the eelgrass abundance. It's popped up here and there over the last 20 years, but not much. What we see on the right graph is chlorophyll A. Chlorophyll A is a molecule that all plants are using to take in CO2 and produce oxygen. So it's a measure of how much phytoplankton or tiny plants in the water column are actually doing that primary production, not on the bottom, not as macroalgae or seagrasses, but now up in the water column. And we see that the water has a lot more chlorophyll A in it in just the last decade or so. And it's increasing, right? So this is the green water that you see out here in the middle of summer. That's what that's an indicator of. These are what we would refer to as algal blooms, right? When you get that really green water. So what we're actually finding more recently is that macroalgae is actually in decline out in the bay. So these are various studies from Ivan Valiella, Jess Sebrian, a number of other studies, as well as the data from the reserve here itself. And when you take all that data, aggregate it together and plot it, we really see declines in macroalgae here in the bay. And what does that mean? That means there's more green in the water column. There's more phytoplankton, those algal blooms up in the water column. So what we're seeing is this shift from eelgrass to macroalgae to now ultimately phytoplankton, these microscopic photosynthetic organisms in the water that are really leading to that green water that we see indicated by those chlorophyll A concentrations. So I call this a shift to pelagic dominance. What does that mean? It just means that the microorganisms in the water are now the dominant primary producers out there. They're running the show. Macroalgae is in decline. We've already lost the majority of the seagrass. And this chlorophyll is really a metric for that phytoplankton abundance. So in that picture, you can see that green sort of brown water. There's no clarity to it. Can't see very far into it. And it's really dominated by these microorganisms. So in these four figures here, this is just showing the correlation of nitrogen over time. So in the two on the left, we have the total nitrogen in the water across the last about 20 years. And no matter if you pool all that data together, if you look at individual sites, it's all increasing, right? So this nitrogen problem remains and it's getting worse. We can plot that same nitrogen data against that chlorophyll A metric, the tiny organisms in the water that are driving that greening of the water. And again, we see a really strong correlation between nitrogen and that chlorophyll A metric of those microorganisms in the water. So nitrogen is driving a lot of this problem that we're seeing. So now to get to the actual title of my talk, we're talking about deoxygenation, acidification, and warming. All of this data has already been introduced to you by Megan. There's a lot of it. It's very hard to get a clear picture out of all of this. And we did a lot of data analysis in the back end. I won't get into it, but I'll just show you the ultimate trends that came out of that data analysis. So water temperatures are increasing, right? They have about 1 degree C over the last 20 years. It's consistent across all the sites. What I'm showing you here is daily temperature anomaly. So what does that mean? It means we took all of the data in aggregate, we averaged it by day of the year over the last 20 years. We subtracted that average out from the total data set. So we ended up with this anomaly number. An anomaly is just what's different from the average. When you plot that over time, you can fit a line to it and you can see here these distinct warming trends across all of the sites. So this is a global impact, right? This isn't caused by nitrogen, right? This is global warming that you're seeing right here locally in the bay. Dissolved oxygen is decreasing, right? We all need this to breathe. Every fish, every crab that is in the water needs this too. And it's pretty concerning that we're seeing an 11% decrease just over the last 20 years in dissolved oxygen. Now, unlike warming, this is both global and local, right? So as that water gets hotter, it can't hold as much oxygen, right? This is like you boiling a pot of water. All the gas comes out, right? Some of that is oxygen, right? So global warming affects this, but actually the majority of this trend is driven by that excess nutrients in the water. So when there's more nutrients, more respiration can occur, and it draws oxygen out of the water. Respiration is just what we're doing right now, breathing, right? We're taking in oxygen, we're breathing out CO2. We see this, again, consistently across the sites. Oh, I'm out of the camera, sorry. Sorry, everyone online. So we also see shifts in the daily patterns among the different sites. So I've been showing you by year in the previous graphs. Now I'm showing you by hour of day. So we've actually averaged this bunch of months of data and years of data, and we've taken it down to what happens across the course of a single day. What you'll see here are the dark colors, the blue colors are earlier years, the yellow colors are more recent years. So what you see is top panel, it's all oxygen. So in the early years in blue, we have more oxygen than we have in more recent years. The bottom panel is temperature. So in recent years and those yellow years, it's warmer across the entire day. And there's some interesting trends that you can pull out here. Like if we look at Sage Lot Pond, which is again out there, it's very shallow. It has these big diel temperature swings, these big daily temperature swings. And the reason for that is because it's very shallow and it gets a lot of sunlight and it can be affected like that. Metoxid in the middle and oxygen on the top is quite interesting. We say there's more stuff in the water column. There's more microorganisms, more phytoplankton in the water column that are creating more oxygen production during the day. And you actually see that in more recent years, right? You get this bigger amount of respiration during the night, and then during the day, you get more of that oxygen production in the middle of the day because everything's up in the water column now. And that's a deeper site, so it's more affected by that. So there's some really interesting trends in here that you can tease out. But again, this just shows that these changes are happening sort of everywhere at all these sites. And it's really driven by the shift to the loss of seagrasses and macroalgae to now being microorganisms in the water. So all of those daily fluctuations in acidity are highly correlated with oxygen, right? So this is that process of photosynthesis where we're producing oxygen, and then respiration at night where we're breaking down all of that organic matter that's made. And this, again, is a really strong eutrophication signal. So when I add this strong correlation between acidity changes and oxygen production, it really just indicates that there's a really strong eutrophication or nutrient enrichment issue in the water. So we just compared oxygen and acidity, and now we're looking specifically at the acidity in Waquoit Bay. And what you can see here again is pretty consistent trends. These waters are becoming more acidic. Again, this is a global and a local problem, just like with oxygen. So we have more CO2 in the atmosphere, more of that diffuses into the water, but we also have those excess nutrients in the water itself, which further creates more acidity. And we see, again, a large change over the last 20 years. So, Waquoit Bay Watchers, I've heard that many of you here are also involved with that. Thank you very much. Here's what all of your data looks like, but I'd just like to highlight that those grab samples that you guys take, which are much lower frequency than what we get in the data sons, we see all of the same exact trends in those data. So if we look at the temperature here, it's all increasing. All of the sites, they're all increasing. If we look at the oxygen, again, very consistent, they're all decreasing. If we look at the chlorophyll A concentration, so take a water sample, take it back to the lab, it gets filtered out for all those small microorganisms that are in the water, they're all increasing, right? Very consistent with the data that I've already shown. So these trends are consistent across all the sampling, all the sensors, all of the different ways we've been measuring these things. So we can take all that data and we can begin to look at some of the more extreme events that are occurring here. So extreme stress events are becoming more common and lasting longer. What's the simplest one of these? Heat waves, all right? We all know what a heat wave is. And basically, we look at the daily temperature maximum and look at how long that maintained itself. And what you can see is that at each of the three sites of Childs River, Metoxic, and Sage La, we're getting more heat waves occurring in the water. We can look at that in terms of oxygen. So how many hypoxic events are we seeing, and are they becoming more common? And the answer is yes. We can do the same thing for chlorophyll. So what does a chlorophyll wave mean? That means an algae bloom, right? This is the green water that you see when you go out in the middle of the summer. And what you see here is a much more drastic increase in recent years. So those algal blooms are becoming more common and they're lasting longer. So now to get into a couple of take-home messages and then also a little bit about what we can do. So we're definitely seeing climate change impacts here locally, right? We're definitely seeing those global stressors. Waters are warming, heat waves are lasting longer, and they're becoming more common. This is likely exacerbating the declines in oxygen that we're seeing out here. And those increasing temperatures and those heat waves are causing more thermal stress, right? Just like you get hot outside in the summer when it's really hot, everything in the water does too. We're definitely seeing eutrophication impacts. Nitrogen pollution is continuing to increase and it's making those impacts worse. The decomposition of all that organic matter that's made by all those organisms results in the production of carbon dioxide and leads to an increase in acidity, right? So that's a global problem, but also a hyper-local problem here where we just have a lot more acidic waters because of that. And then there's combined effects of those two, right? So we have longer lasting hypoxia events. That's excluding a lot of mobile organisms from our waters here. We have this shift from benthic macrophytes to this pelagic phytoplankton community, right? So we don't have seagrass anymore. We don't even have macroalgae anymore. We just have green water that phytoplankton reside in. This loss of benthic species has led to estuary-wide degradation, and I'll talk a little bit more about why that is on the next slide. But Sage La Pond used to be a pristine site. A decade ago, I used to use that as a pristine site. right? There used to be a big seagrass bed out there, and I would go there to do research because it was a nice site to work in. So what does this mean for management? Eutrophication continues to degrade ecosystem function and structure. So we've seen this large shift in what the dominant primary producers are out here. Seagrasses and macroalgae, they're sessile, meaning they stay in one place for the most part, right? And what they used to do was they used to grab all those nutrients and take them in to build their biomass. And now they're not stuck in Childs River or Sagelot Pond. Now we have this phytoplankton biomass, this pelagic biomass that just lives floating around in the water. And that gets transported throughout the bay. It goes everywhere, right? So Sagelot Pond, which has very low nutrient inputs, now has a large influx of those algal blooms. And that's leading to degradation even at places where there's not big nitrogen impacts, right? So now we've got this mobile eutrophication, if you will, this mobile amount of biomass of bad water quality that is readily transported throughout the bay instead of being captured by those macrophytes, those big plants that would normally remove that in place, which has really led to estuary-wide degradation. So they're hydraulically connected. That's what I just explained, right? And because that's so mobile, living up in the water column, it easily gets transported throughout the bay. So we kind of have a new state of degradation now, right? We would really call this a pelagic dominated system, unfortunately. It's unclear how quickly the ecosystem will recover when we do get those management implementations in place. Will it take till 2040 to get sewers out here? I'm not sure. I'm not a politician. I can't answer that for you. But we don't really know how the ecosystem will respond to that in the future. So managers must remain vigilant and continue monitoring these systems, this water quality, until the habitats actually respond. So of course, we always need more research to understand it better. We of course need restoration of the system, and conservation is definitely needed. And it's really critical to the long-term health of the estuary. So what else can we do? Sorry, I don't have a great story for you tonight, but that's what the data tell me. So you can advocate for this, right? We know sewage treatment works quite well, right? So you can advocate, you can vote, right? You can make this happen to try and get the implementation of sewage systems a little bit faster throughout the Cape. There's a lot of talk right now in the local news, right, about denitrifying septic systems and potential rules that the Massachusetts DEP is trying to implement to get denitrifying septic systems in. So what does a denitrifying septic system do? It takes that organic nitrogen pollution and it converts it to N2 gas. What is N2 gas? Dinitrogen gas. It makes up 79% of our atmosphere. It's inert, right? So this is a great thing. If we can take that pollution and convert it into a gas that makes up the majority of what you're breathing right now, that's a good thing. There's a lot of information out there on denitrifying septic systems, right? And if you really want to know, I encourage you to read a paper by one of my colleagues, Chris Gobler. He tested this up here at our sewage treatment plant in West Falmouth, and they work quite well. So if anybody is worried about sort of disinformation about whether these denitrifying sewage septic systems work or not, I encourage you to read this paper. I'm happy to send it to anyone that wants to reach out to me. So kind of a crazy idea I've had recently. You know, thinking a lot about seagrass restoration. How can we kind of get seagrasses back, especially as we begin to improve that water quality? What can we do to kind of give them a jump start to get back into the ecosystem? So this is a project that I'm working on right now. It's called a SMRP, which is a great name, right? Everybody loves a SMRP. So it's called a Seagrass Meadow Underwater Restoration Platform. The idea, there are a couple of ideas here. One of them is that denitrification, right? If we can create a little bioreactor with seagrasses where they take in that organic nitrogen pollution and convert it back into the atmosphere, right? So we're trying to create a little bioreactor here with seagrasses. They also remove a lot of pollutants. They'll remove those microorganisms from the water column just by the function of their blades. They make the water clear. And the other idea here, you can see I had buoys attached to this system, right? The thing that really limits seagrass growth is light, right? When you have that green microalgae in the water growing, there's just not enough light for seagrasses, right? So what do? We can move it up higher in the water column, get it more light, right? So this is an idea that I've had for a while. We're working on it right now. We're running trials of this in our seawater facilities at Woods Hole. We've got thousands of seagrasses that we collected seeds from local seagrasses here, and we have them sprouted in the lab. We're planning these out next week, and we're looking for places locally to deploy them. So I'll talk to Megan later about this. So there are some things we can do. You know, not all of it is lost, but we do have a lot of work to do as a take. So I'd like to thank Jordan. That's a picture of Jordan here. She really helped give me a lot of the historical knowledge about the program. Helped me understand how it changed over the years, where some of the data may have been problematic, and I wouldn't have been able to do that analysis without Jordan. Of course, my whole lab, you know, we do a lot of work out here. We do a lot of testing, so you'll see us out here sometime. Feel free to reach out to me. My webpage is there. And that is the actual paper that has all this data in it. I'm happy to send that to anyone who is interested in reading a very verbose scientific paper. Thank you.
Thank you so much. That was, it was good to hear, but it was really clear and sobering to see all the data and what's been happening over the past few years. So I'm sure people have questions now. So here's the way we're going to do that. In the room here, I've given people cards so you can write down if you have any questions on the cards that I gave out. And but we'll start with the Zoom group. How many people are on Zoom? All right, so we're going to start with their questions first, and I'll give you guys a chance to write down your question. And then, it could be for Matt or it could be for Megan if it's a general about the swamp data. And so if you want to come up here, and I'll just hand you the questions and you'll have to read them out so the Zoom people can hear.
I'll start with a question.
Sure.
There are now 3 full-size shellfish farms in nearby rivers in Falmouth. Do these farms help remove or reduce nitrogen in the bay? And also, since there are no septic homes near Sage Lot Pond, why is that area degrading as much as the others in the bay?
Sure. So shellfish definitely will filter out all of those plankton, all those tiny organisms in the water. They convert that into their biomass. They also convert that into waste locally, right in your system. Now, if you can take those shellfish out and remove those nutrients from the system, then you're effectively removing nutrients from Waquoit Bay. But that's not a super efficient way to do it, but it definitely helps. The second question is, there's no septic systems in Sage Lot Pond, so why are we seeing degradation there? The answer to that is because we have all of those plankton, all of those little tiny photosynthetic organisms in the water. They're no longer being captured by seagrasses or macroalgae in Childs River or just offshore here. So all of those nutrients are now being transported into places like Sage Lot Pond, leading to degradation there. So because we don't have those big macrophytes that are taking nutrients up where they come out of the groundwater, now it's just all in the water and it gets sloshed back and forth by tides. And that's leading to degradation in a place like Sage Lot Pond, where there isn't a lot of septic systems.
Another question, do vegetated buffer strips along the shoreline significantly help reduce nutrient loading?
That's a good question. So yes, certainly having plants along the shore will definitely be helpful. Where the groundwater comes in, which is carrying all the fluid from your septic systems, a lot of that happens right at the water surface. So having plants in a riparian zone, which is what we call sort of the area right next to the water, certainly help to remove some of those nutrients. Yes, certainly much better than a fertilized lawn going right up to the edge of the water.
You can read this out loud.
Sure.
Everybody can hear.
Where is Childs River in the monitoring station? So that was a question, right? Where is the monitoring station was the question, I think, right?
Where in?
Oh yeah, so 128 crosses over right here. That's Childs River, and it's just south of the bridge on the docks there, right? Yeah, in the marina. Sorry, that's like a Jordan question or a vegan question. I just analyzed the data.
Beyond the water chemistry conclusions, are you able to offer any thoughts about how these evolving conditions have quantitatively affected Waquoit Bay fish and shellfish?
No, is my answer to that. So why do I not have an answer to that? Well, I don't have that data specifically, right? I don't have any data on fish, on crabs, and WBNERR doesn't monitor those directly, right? There's been a lot of studies in the past that have monitored that, and we've seen those previous declines. That's where first few slides where I was talking about scallops, I was talking about clams, I was talking about fish, and decapods in the system. So I don't have any direct evidence of that, but I'm building on a large body of evidence that those were the first things we saw disappear from Waquoit Bay, right? The scallops disappeared first, the seagrass went. You know, we saw declines in fish, we saw declines in crabs, right? And those are really those big warning signs that we see visually with our eyes, right? But you can't see a change in oxygen with your eyes, right? And these are the like ultimate bad changes that we're seeing from that water quality degradation. Oh, this is a long one. Untitled River, that's how you say that, right? Sorry, I've only Municus, I was getting it wrong. Untitled River has clumps of brown yuck, right? In spring, early summer. Yep. If it was harvested, would it help the health of the river? What to do with the harvested yuck? That's a great question. Harvested, yes, if you could remove that, what is that floating material? Brown yuck is not a scientific term, but I could guess that it's probably benthic mats that actually produce gas. So they would be photosynthetic organisms that grow on top of the sediment. And what happens is they photosynthesize, they make oxygen, they actually make bubbles, and they get caught inside of that microorganism mat. And what happens is that mat floats up to the surface, and that's the brown stuff that you're seeing on the surface of the water. So it's a whole bunch of microbes basically that live on the bottom. They then float up when they make too much oxygen basically. And then they're just kind of gross stuff floating around the water that nobody likes to see. So could you net that out? Sure. Could you take it to the landfill? Yeah, that would be an effective way to do it. Is that effective at scale? Probably not, but maybe it could help. It's a good idea. How do you compare conditions in Waquoit Bay and Nantucket Sound? Is there eelgrass outside of Waquoit Bay? Yes, there is eelgrass right outside of the inlet. So how do I compare them? I had that very early slide at the beginning of my talk where we saw these flat lines in oxygen and pH and these big variations in Waquoit Bay. That's really because the area just outside of Waquoit Bay is very well flushed, right? Tides are coming, it's mixing with Vineyard Sound, the water is very deep out there. And in here, we have a very shallow water column with a lot of primary production. That's why you get those big shifts. And that is what is hurting a lot of these organisms that live in Waquoit Bay. It's those big shifts, right? It's those hypoxic events. It's those heat waves that are really excluding the organisms from living in Waquoit Bay. Now, right outside of the inlet to Waquoit Bay, it's very well flushed. You know, there's no Nantucket Sound water coming in with every wave. And this goes back to an adage from the early 70s that dilution is the solution to pollution, right? And that's effectively what's happening on the coast right out there, but that's not what's happening in Waquoit Bay. There's no dilution, it's just accumulating inside of the bay. I'm not advocating that as a way to get rid of pollution, to be clear, that's from the 70s. But it's a very useful mechanism for describing the difference between the water right out here and the water out in Vineyard Sound. That was great, lots of questions. Why, what is the variation in salinity across the sites? I might even have a slide for that. Yeah, here we go. The variation in salinity across the sites, not a whole lot until you look at Quashnet River. So Quashnet River has changed by 2.5% per year. So why is that? It's because restoration has happened upstream on the Quashnet River. There's been dam removal. There's been restoration of cranberry bogs upstream, I think. And that has actually led to a large change in salinity over the last 20 years because some of that natural water flow is being restored. So how does it vary across the sites? I don't think I have averages on here. Nope, so that's not useful. And I don't have a direct answer to your question, but I can certainly get that from
for the 4 SON sites, it's very low variation. Even Child's River is pretty high. So it's kind of.
They're very similar.
You might repeat what you said.
They're very similar, says Mika. She knows. How is calibration maintained over a 20-year period? That's a great question. There's a whole protocol for how you calibrate these data sondes. They come in and out of the water, every 2 months about? 30 to 45 days, there you go. So there's a very detailed protocol making sure that the data that we get out of those sensors is very accurate. There's also post-checking of that data that happens. So quality assurance that that is actually really good data coming out of all the sensing systems that they use here. Is eelgrass thriving anywhere? If not, why? And converse. Yes, eelgrass is thriving in many places. Right now, I have a long-term flux monitoring station just off of Noshawn Island, just outside of Woods Hole. And the eelgrass is there doing great. It's a very well flushed site, so it gets fresh water from Buzzards Bay on every tidal cycle. Out there, the seagrasses flower, they produce seeds. And seagrass is just like grass in your lawn. It has pollen, they have seeds, they have flowers. It's a great plant. It evolved from land about 70 to 100 million years ago. So you can think about it just like the grass in your front yard. So yes, it's certainly thriving some places, but definitely not right out here.
Question from online. Pleasant Bay on the Outer Cape is doing much better than Waquoit Bay, but there is still a 60 to 80% loss of seagrass. Can we test some of your eelgrass growing smurps in Pleasant Bay?
I would love to, yes.
Okay, we'll get you two in contact. I'm going to give you another question. Thank you for an informative session. Seagrass restoration efforts across the state to date have been challenging. What about synergistic effects from organic matter buildup in the sediment over many years that can also lead to sulfide production that could potentially be harmful to seagrass growth?
Yes, so sulfides are toxic to seagrasses, right? They're very common in the sediments. Even if you don't have a lot of nutrient pollution, you will have very sulfidic sediments wherever you have a lot of organic matter. That's what seagrasses do. They trap organic matter just by the structure of their blades. They trap particles. That increases the organic matter in the sediments. It leads to sulfidic sediments. Now, where that really becomes a problem, what seagrasses do is actually pump oxygen out of their root system. So they have roots, again, just like the grass in your front yard, and they actually pump oxygen from their blades up in the water column down into the sediments. Now, what happens when a hypoxia event comes by? What happens when the oxygen in the water is really low? They can no longer pump that oxygen into the sediments because they don't have any. This happens at night really commonly, right? And that's when you actually get the die-off of the seagrass, when you have that hypoxic event combined with high sulfidic sediments. And it's those acute events are what really kill the seagrass.
All right, this may be the last one. Raise your hand if you still have a card for me.
There's a lot of seaweed in northern Waquoit Bay. Is it practical to dredge the seaweed to help the eelgrass? It's an interesting idea. So seaweed, I mean, depends on your definition of seaweed, right? Some people consider seagrass seaweed, but here we're talking about macroalgae. So could you dredge that up and would it help the seagrass? Well, certainly if there's still some seagrass there and you're dredging up that macroalgae, you're definitely not helping the seagrass because you're also dredging up the seagrass itself that might be there, right? But could you gather that up and remove it as a nutrient removal strategy? Yes, you probably could. You know, a lot of these ideas, even my SMRP idea, right, doesn't really get to the heart of the problem, which is that nutrients are still coming in the groundwater, right? Even if you remove it at the end point, that end result where it's bad, that doesn't really affect the core root of the problem, which is we have way too much nutrients coming through groundwater from all of our septic systems. So it's kind of a short-term solution, all of these are. These are great questions, by the way. I would think on my feet a lot. What would it take to implement the N2 gas septic systems? Well, I will let the politicians handle that question, but I do want to explain a little bit of what a denitrifying septic system is. So we all have septic systems on our house, except for maybe one or two of you, just based on the numbers. And really what a denitrifying septic system is you put wood chips in when you build it. That sounds a little wacky, right? Like, why are you putting wood chips in your septic system? Well, it really provides a carbon source for microbes to grow. And it creates this oxic-anoxic boundary in the sediment where the microbes live. And where denitrification happens is that anoxic-oxic boundary. It needs a source of oxidized nitrogen to convert it into N2 gas. So in the simplest sense, they're really simple, right? There's not a lot to denitrifying septic systems. They're hard to monitor, they're hard to upkeep, but in the simplest sense, implementing them, especially for new construction, wouldn't be that difficult from my scientific perspective. Now, how the politicians deal with that is not my thing.
So, it's at our witching hour here.
Sure.
So, thank you so much for a really excellent presentation, very clear. And I just want to let everyone know that we will be posting all 5 of the presentations on our website. And actually last week it was about permeable reactive barriers and such. But I think that they'll also become this will also become a very good resource for people to be able to look up in the future. So I think we're gonna close the recording now. And if people here want to have more discussion, that's fine. But this way we have sort of a nice package for that to put on the web. So thank you very much.